Here we look at the derivative of a power function, and we're going to pick up on a pattern here for these particular types of functions so that we can avoid using the limit definition of the derivative. So what is a power function? So here are some examples of power functions. Y could be x squared, y could be x to the third, x to the fourth. Those are all power functions, but so are things like x to the negative third, x to the 1/2, etc. So the key here is that your exponent, sorry, that was supposed to be a highlighter, the exponent is a number and the variable is in the base. Okay, these are exponential functions. Two to the x, 3 to the x, 4 to the x, 1/2 to the x, and there's a reason that I didn't write -3 to the x. Those are exponential functions, and we are not going to be looking at the derivatives of those. Okay, those are much harder to deal with. So we are only looking at power functions as we've listed above. So let's begin first of all with the simple case f of x equals c. This is not a power function, it's a constant function, but I did not want to create a video just for a constant function. F of x equals c, then f prime of x is 0. And we will verify this with the limit definition of derivative first, which happens to be the limit as h approaches 0 of f of x plus h minus f of x all over h. Well, this is the limit as h approaches 0. F of x plus h, well, the output for this function given any input is c, so f of x plus h is c, minus f of x is c, all divided by h. So we have the limit as h goes to 0. This fraction ends up being 0 because c minus c is 0. So if the limit as h goes to 0 of 0, which in fact is 0. Right? 0 is going to equal 0 no matter what h is. So there we go. We've just shown that the derivative of a constant function is 0. Okay, let's look at a more interesting example perhaps. F of x equals x. The derivative of this function is the constant number 1. So let's take a look at why that is. We'll do the same thing. We'll apply the same limit definition here. We'll do it a little quicker this time. F of x plus h for this function is x plus h, minus f of x is x all over h, and we can see that the x's cancel out, leaving h on top, and then h divided by h is 1. And I apologize, I forgot my limit. How terrible. Right? We always tell our students not to do that, or if you are a student, we tell you not to do that. And then here I go. So I forgot to say the limit as h goes to 0. It's a bit irrelevant anyway because the h is canceled leaving behind 1, and so the limit is 1 as we wanted here. The derivative of the x function is 1. Let's look at f of x equals x squared, and actually I'm going to need some more room, so I'm going to move this stuff out of the way. The derivative of x squared is 2x to the first, or just 2x. So let's see why that is true. F prime of x equals the limit. You're getting the hang of it, right? As h goes to 0 of f of x plus h, which in this case is x plus h squared, minus f of x, which is x squared, all over h. Then, if we multiply this out, and I'm not going to actually multiply this out, I'm going to start establishing the pattern that we want to observe. The limit as h goes to 0, this is going to be x squared plus 2hx plus dot dot dot. Really, this is just h squared, but I'm putting dot 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 to observe the pattern, minus the x squared over h. Now, you'll see why in a moment that this stuff here is not important, and I'll mention right now that everything that I've left here, every term contains at least h squared. Okay? So now, if we think about how we would evaluate this limit, well, x squared minus x squared drop off. Okay? And look at my 2hx. So I've got 2hx plus dot 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 Again, the dot 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 part contains at least h squared. Again, if you're not seeing what's going on here, that's okay, you'll see soon. So we have the limit as h goes to 0. On top we could factor an h out, right? Because everything on top has h. So if I factor out h of the first term, I'm left with 2x plus dot dot dot. Now, what can you tell me about the dot 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 if I factor out h? Well, it used to contain at least h squared, but I factored an h out, so now it contains at least h. Alright, maybe you're catching on. This is all over h. I cancel my h's, and I'm going to keep writing it here. I've got the limit as h goes to 0 of 2x plus dot dot dot. Now why is this so nice? Everything here, all the missing terms that I don't care about, contain at least h. That's precisely why I don't care about them. Because when I take the limit as h goes to 0, all this stuff goes to 0 since it contains h. So up here it was vital that it contained h squared because I knew I was going to factor an h out and I wanted an h to remain. So after I take my limit, this stuff goes to 0 and you can see that I'm left with just 2x. Okay, very good. Let's do the same thing for the x cubed function. First, I suppose I should point out a couple things. When I expand this, the first term, x squared, would always cancel with itself on the end. You notice that, right? So these guys went away. So this first term is always going to cancel out when you multiply. Secondly, this number here in front of the second term is the same as your exponent. If you've seen the binomial theorem, you would know that this second number is always the same as the exponent. So that's pretty important here because you'll see when we do x cubed, the same pattern holds. So the derivative of x cubed is 3x squared. We'll go through the same process, except we'll try to speed it up a little bit this time. The limit as h goes to 0 of x plus h cubed minus x cubed over h. Well, just what I said a minute ago with that last example. I know when I expand this out, I'm going to get an x cubed, which is going to cancel with the negative x cubed on the end, right? Those are gone. And then I know my second term when I multiply, when I cube this thing, is going to start with a 3. So it's going to be plus 3. And I had x cubed here, so this is going to have an x squared. And it's going to have an h because the exponents of those two things have to be 3. Every term in the expansion of this has to have the exponents add to 3. Again, this is due to the binomial theorem, which you could investigate on your own. Now I'm putting my infamous dot dot dot, right? We like this. What can we say about this dot dot dot? Well, this was h to the 0 in the first term. This is h to the first. So everything here contains at least, can you guess? Contains at least h squared again. Okay. Over h. Okay, let's get moving here, right? On top now, I can factor h out. And that leaves 3x squared plus dot 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 over h. And now the dot 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 at least contains at least h. These h's cancel. When I take the limit as h goes to 0, since all of this stuff contains at least h, all of this goes to 0. And you can see that I'm left with just the 3x squared, which is exactly what we wanted. Alright, if you did x to the fourth, you'd have the same thing. You'd have 4h x cubed here, right? So the general pattern, if you haven't caught on to it, so we have f of x equals x squared. The derivative is 2x. F of x equals x cubed. The derivative is 3x squared. F of x equals, and I just mentioned it, we haven't actually seen it worked out, but we could imagine that it would be 4x cubed. Dot dot dot, the general pattern is f of x equals, if you don't see it, the way this works is, you drop the exponent down to the front, so that's where the 4 comes from, and then the 3 is what you get when you subtract 1 from this exponent. Drop 3 down to the front, right? and then you reduce the 3 by 1 exponent, so you get a 2. Drop your 2 down to the front. Reduce your exponent of 2 down to 1. Alright, good. So if you have x to the n, what's the derivative? Well, f prime of x would be, drop your exponent down to the front. Hey, this looks like a logarithm law, right? N times the base x, and you reduce your former exponent by 1, so n minus 1. Okay, so some examples you may want to try. Here's the general pattern for power functions, finding the derivative. You may want to try these examples and see how you do. Number 1, see if you can find the derivative of the function f of x equals 1 over x. And recall that 1 over x is simply x to the negative first power. See if you can find the derivative of the function square root of x, and recall that square root of x is x to the 1/2 power. Okay, so give those a shot. Have fun with it.